All right, I believe it's recording. Hopefully it works out. So let's talk about this. This sheet is just the core skills to trig. Whatever is literally need to know, nothing more, nothing less, with different conditions, because generally you need to know two main facts. You need to know your reciprocal trigs. One of the reciprocal trigs, like uh, sine x is equal to 1 over cosecant x, and you have a sheet of all those. The other thing you definitely need to know is your Pythagorean identities. Sine squared plus cosine squared equals 1. And the fact that you can manipulate that and use that is important. Both are on the formula sheet, on the top of the formula sheet. It will be a quest. It's only 3 sections. All right. First one. First, I don't know how to call it hint or tip or strategy, whatever you want to call it, is to turn trig into sines and cosines in order to simplify. Cotangent, I could convert cotangent into cos over sine. Cotangent becomes cos over sine. Cosecant is 1 over sine. Because they're both over sine, I could cross these out, which means my final answer is cosine. If along the way you forget the x's, I'm not going to be a stickler, but make sure you put that x or theta or whatever symbol I use at the end. So that's the first one. Sometimes we have to use the Pythagorean identity. So over here, secant squared minus 1. Now, if you look at the formula sheet, there's this Pythagorean identity, tan squared x plus 1 equals secant squared x. Usually it looks like this. Remember, with a Pythagorean identity, you could rearrange it to your benefit. So I could rearrange it as tan squared x equals secant squared x minus 1. Since it equals secant squared x minus 1, it equals tan squared x. So I could replace this with tan squared x. So cosine squared times tan squared. Well, tan, I could rewrite cosine squared x as sine squared x over cos squared x. And since I have a cos on top and bottom, I could cross those out, which means my final answer is sine squared x. Let's use the next one, using factoring. You can use factoring like a GCF or quadratic factoring to solve some of these things. For example, both of these have a secant squared x. So what I can do is using the GCF, factor out secant squared x. So I could rewrite it as secant squared x equals tan squared x plus 1. Well, earlier I said tan squared x plus 1 is secant squared x. So I could rewrite this as secant squared x. Secant squared times secant squared. Think of it like a variable. X squared times x squared would be x to the fourth. So secant squared times secant squared is secant to the fourth x. That will be your final answer. As simple as possible. Hmm? Cosine? No, 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 no. Because there'll be 1 over cosine, which is not definitely what you want. Cosine, turning into cosine and sine is a strategy you could use to simplify the stuff. Your final answer might be sine, it might be cosine, but it might not be. You definitely do not want to end with a fraction especially since you can reciprocate things. So definitely don't end with a fraction. What do you mean? Well, let's no. So this is the difficulty of this section. Right now, I see in this, and I'm like, yo, I just did 2 questions with this exact tan trig Pythagorean identity. Should I change this to tan squared? Because I said it like that, probably not. So my other move I'm going to do, think of this as x squared minus 1. If it was x squared minus 1, I could factor that into what? So it works the same way with secant. I could rewrite it as secant x plus 1 and secant x minus 1. Now, because I see a secant x minus 1 on both top and bottom being exactly the same, it's no longer squared, it's because it's exactly the same, I could cross this out, which means the most simple thing I could rewrite this as is secant x plus 1. That's I wish I could say you could do that. This is the hard part about this section. You no, don't change. That would be unsimplified if it's a fraction. That'd be unsimplified if it was a fraction. If you did a question randomly and you got like 1 over sine as your final answer, you should convert that to cosecant x. You should convert that. Okay. You can't do anything else. This is not squared. It's not the one is not a thing that you could that's I wish I could say it always will end with one trig function of some sort. I can't promise that. That's the problem with this thing. There's no hard rules. These are strategies more than what we usually do with, which is formula slash algorithms. So let's talk about it. This I could rewrite, and if you ever have trouble with the factoring, just rewrite it as variables. X to the fourth plus 2x squared plus 1. Looking at that, it's a type of difference, or I shouldn't say difference of squares. It's technically a sum of squares. I could rewrite this if it was x's as x squared plus 1 squared, because you would FOIL it out to get that. So tan squared x plus 1, all of that squared. Thank you. All right. So because it's that, wait a second, tan squared plus 1, that feels familiar. Secant squared. So always keep your eyes open for something like that. And like I said, I wish I could just tell you, you did it. There's no answer to that. Secant squared squared, you could think of it as x squared squared. So secant to the fourth. And that's your final answer. Nothing more to simplify. Funny enough, this is equal to like 2 questions ago, right? Yeah. Interesting how that works. All right. 5.2 is about verifying trigs. I'll call it 5.2 because that's where it is in the book. So in this situation, a little bit different than the previous thing, you already know what answer you're going to. You have to get there, especially for this section. And I wish I could grade these faster. It will take a little bit to grade these because I have to look at every step of your work. I can't just see, oh, you got the right answer. See, I got to see every step. So it takes a little longer to grade up front. For this part, for the trig stuff? Well, I wouldn't say that on a recording, man. So this is. So who knows? Overall, it tends to be easier to make a larger trig expression. Again, these are strategies. These are the strategies. Overall, it's easier to make the bigger thing into the smaller thing. So in this case, I'm going to work on the left side. So in this case, I have two fractions here. In order to add a fraction, what do I need to do? Good. So this guy needs a 1 plus sine x on both the top and the bottom. And then this guy on the right, he already has a 1 plus sine x. So he's going to need a 1 minus sine x, both on top and bottom. So on the top, it's going to be 1 plus sine x plus 1 minus sine x over, remember, this is technically being multiplied. So you could FOIL this, but hopefully you see it's a difference of squares. So I'm going to rewrite it as 1 minus sine squared x. That's fine. If you FOIL it, you would eventually get that anyway. So, all right, let's continue. Condense things. I see 2 here, so I'm going to make this 2. Sine x minus sine x completely disappears. So it's 2 over 1 minus sine squared x. Not now, buddy.
We skip a step.
Depends. I'll show you what, like, I'll finish this and I'll show you what I wouldn't mind you skipping. Okay. So then over here, 1 minus sine squared x. Oh, 1 plus 1 is 2. And then the signs subtract each other. Because it's sine minus sine, yeah? Yeah. Combine like term. Now, 1 minus sine squared x, using the Pythagorean identity, is cosine squared x. Did we do this already earlier in the video? I think we did with the trig at least. This 1 minus sine squared x equals cosine squared x. We did it with secant. It's the same thing. And then, wait a second, cosine's on the bottom. I'm not really want that. And plus, I know what I'm looking for anyway. So I'm going to bring it to the top. When cosine goes to the top, it becomes secant. So secant squared x, which matches what I was looking for. So box it off. You're good. In terms of questions of what can I skip, I would need to see this for sure. But you could have skipped all the way to here, and I would be okay with that because you're doing something different to the top and the bottom separately. But now, because now the top and the bottom are interacting, then I would need to see that stuff. Okay. So you could skip that little middle one, I guess. Yeah. All right. Again, these are just strategies. Overall, it tends to be easier to make a sum into a product. So tan plus cotan equaling secant times cosecant. In this case, I'm going to change this one. Good. So I'm going to change tan into sine over cos. This thing? This is like strategy. Remember. Oh, you have in this situation, one side is pluses and one side is multiplying. Earlier, I feel like earlier is a little obvious that I would rather make this big thing into the small thing. In this case, if you have a choice, because they're technically the same size, two trigs, if it's between a sum versus a product, I think easier. Yes. Overall, I think it's easier. And again, yes.
It's not like a hard one.
No, you could have done it the other way. You could do it the other way. I think it's harder though. Because then you have to split a fraction correctly, which is kind of hard to do. So this guy needs a sine. Mm-hmm. Yes, sadly, this is a lot of writing. But your test doesn't have that many questions, which I know some people don't like that, but you know, if you do 3 of these, you prove that you understand this thing. Not yet. I know what you're trying to say, but not yet. Oh, sine times sinus is times. It's times.
Wait, so
So the Pythagorean identity on top makes sine squared plus cosine squared equal 1. Sine x, cos x. Wait a second. I know I'm going to secant and cosecant. When I move sine up, it becomes cosecant. And when we move cosine up, it becomes secant. So now I could just rewrite this as cosecant x times secant x, which matches the thing on the other side. You don't have to like flip it or anything like that. I'm gonna use a straight on that. Any questions of that? I kind of did stop talking. I was just working on it a little bit. So looking at the red, I have cosine as the denominator here and sine as the denominator here. Oh, I just realized my mistake. Thank you. So I need a sine to make this the same as this. Yeah, go ahead. And this guy, I needed a cosine x on both sides to make the denominators the same here. Once I do that, sine times sine is sine squared. Cos times cos is cos squared. And then sine times cos, that's just sine times cos. There's nothing special about that. And then from there, I think I cleaned it up. Yeah. All right. My third strategy, when you have a difference between a sum and a quotient, I think it's easier to change the fraction into addition or a sum. It could be a difference too, I guess. But both are reasonable. You could technically go either way on this one. It doesn't matter this one too much. I'm going to try to do from the right side. So cos equals 1 minus sine. And let me just pull up this thing because I want to make sure I don't. For a video, I don't want to step up. Yeah. Okay. So in this scenario on the right side, I have 1 minus sine x. It's so close to being something useful. If it was 1 minus sine squared x, I could convert that. So why don't I do that and make it that?
So multiply times on.
So I'm going to multiply both sides, or top and bottom, by 1 over sine x, 1 plus sine x. There's a purpose for this, right? It's okay. Well, I don't want to foil, actually. I'm going to leave it like this for now. So cosine x times 1 plus sine x over 1 minus sine x times 1 plus sine x. Again, is a difference of squares. So it's 1 minus sine squared x. Since it's 1 minus sine squared x, I could rewrite that, manipulating the Pythagorean identity, as cosine squared x on the bottom. Because I have a cosine on top and a cosine squared on bottom, I could cancel out the cosine on top and reduce this to a power 1. So it's going to become 1 plus sine x over cos x. Remember, I'm going to have what I'm looking for is two things are being added to each other. So I'm going to split this as 1 over cos x plus sine over cos, both of them x. Because I'm going to split them into two plus signs. Well, lucky for me, cosine, when I move it to the top, becomes secant. That's secant x. And sine over cos is tan x. And now that matches what I had. This question is a good example that you could technically have done it either way. Okay. I'm not going to do it both ways, but you could technically have done it either way. Okay, let's go to the last part, which is 5.3, which is solving. In the instructions, I say typically, but I made a test. It's going to say from 0 to 2 pi. So you want to give me every instance where this is true. You're using the idea from the Pythagorean, the unit circle, okay? So let's say we have 2 sine x minus 1 equals 0. Your goal, just like if it was a variable, is to get it by itself. So you could do plus 1 plus 1. So 2 sine x equals 1. Divided by 2, divided by 2. Sine x equals 1/2. Now that's pretty useful, but that's not technically my final answer. What I need to figure out is what values for the angle, like what degrees or what radians, causes it to be a half. Okay, causes it to be a half. If you remember the unit circle, at 30 degrees, it would be sine, the y value would be a half. Depending on what quadrant you are, it would be 30, 150, 210, or 330. But remember, I'm looking for positive a half. So the angles I should be looking for is 30 and 150. But I do ask in radians. So you got to make sure you be able to convert it or remember it as radians. 30 degrees is pi over 6. And 150 degrees is 5 pi over 6. By the way, if the denominators match, you know you're talking about the same reference angle. So the fact that the denominators match is really good for you. So my two answers is pi over 6 and 5 pi over 6. This is where I could plug in that would cause sine to be a half. Remember, just like a variable, you're just trying to get the variable by itself. In this case, whatever the trig function is. In this case, sine. So I'm going to do plus sine x plus sine x. So I got 2 sine x plus root 2 equals 0. Get sine x by itself. Subtract root 2, then divided by 2. I have negative root 2 over 2. So what angles are sine at root 2 over 2? Well, that would be at 45, 135, 225, and 315. Since this is negative, I want the negative where sine is, which happens to be in the third and the fourth quadrant. As radians, that's going to be 5 pi over 4 and 7 pi over 4. Again, be confident with your unit circle.
No, we have unit circle.
But where have you been?
Next one. Looks familiar, but now it's cosine squared. Let's see how that changes everything. Plus 1 plus 1. So 2 cos squared x equals 1. Divided by 2, divided by 2. Cos squared x equals a half. Now I need to square root both sides because technically cosine is not by itself yet. So I'm going to get, put over here, cosine x equals plus or minus. When you square root a fraction, you can square root the top and bottom separately. The square root of 1 is 1. With the square root of 2, we're just going to write root 2. But what's the problem with a square root on the bottom? We don't like that. So we're going to clean it up and rewrite it as root 2 over 2. Okay. Now I need the places where cosine x equals root 2 over 2. That happens at the 45 degrees. But in this case, since it's plus minus, I want it where it's both positive and negative. Luckily for me, there's no third symbol. That's every instance that is positive, negative. So that's going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So if you have a plus minus, it kind of relieves the quadrant thing. You just put them all. So your final answer is this. Okay. Let's tackle this last one. This is the last one. Good. Let's tackle this last one. Remember, our goal is to get the trig by itself. But what's weird about this is I have a cotangent and a cos. Well, let's see what I could do. This is 2 cotangent x. Yeah. It's these 3 sections. It's just these 3 sections. My test is a slightly longer form of this review sheet, basically. All right. So in this case, I have 2 cotangent on both sides. Because I have cotangent on both sides, it's kind of annoying. So how do I leave that? Well, if I divide cotangent here and I divide cotangent here, then they cross out. And now I don't have to deal with them anymore. So it comes cosine squared x equals 2. Square root both sides. Cosine x equals root 2. Now, I messed up the writing of this question. I must have done because it would work for cosecant, but this doesn't work for cosine. Did I miswrite this? Or miswrote this, I should say. Yeah. Okay. So in this situation, you might notice, wait a second, square root of 2, there's nothing down on the unit circle square root of 2. So you want to say no solution. Okay. And if it was just square root of 2, you're right, it would be no solution. But we have to keep in mind something else. So I'm going to rewrite the question to show you something else. So what if I did it this way? Where instead of dividing cotangent on both sides, I subtracted 2 cotangent x. What happens differently? So in this case, because I have 2 cotangents, I could factor it out. So I have cotangent x times cosine squared x minus 2 equals 0. Because this is a factor equals 0, I could split and solve this. Over here, we already figured out cosine x equals the square root of 2. That's a no solution. But over here, cotangent of x equals 0. In this scenario, I do have some solutions. So your solutions where cotangent 0 is basically when the slope is undefined normally. It's going to be at pi over 2 or 3 pi over 2. So the question is, which way do I do it? You have to do it this way. No, it's not no solution. You cannot do this. The reason I'm pointing this out is that's not allowed. You can't just divide the cotangent. You don't want to eliminate it like that. You want to subtract the 2 cotangent x and then factor, okay? Just to be clear, right? So your answer is pi over 2, 3 pi over 2. Oh, and I guess probably it's not obvious why cotangent is pi over 2 and 3 pi over 2. Remember, cotangent is cosine over sine. Because of that, I'm effectively finding equals 0. I'm effectively finding when is cosine 0? Well, cosine is 0 at pi over 2 and 3 pi over 2, which means cotangent is also 0 at pi over 2 and 3 pi over 2. All right, that covers everything you need to know for your little test. Quest, I guess I should say. Any questions beforehand? Give me a second. What's up? Yeah, quest. Trick